Module 9.2. As a reminder, it's recommended to print the video script and annotate the script while watching the video for later use. Video scripts are available on Canvas. Module 9.2. How can we numerically describe the relationship between two or more variables? Previously, we saw different numerical summaries for a single quantitative variable, such as mean, median, and standard deviation. There are also numerical summaries to help us with two quantitative variables. How can we numerically summarize the relationship between two quantitative variables? The correlation coefficient is a numerical summary of the direction and strength of linear associations between two quantitative variables. If the correlation coefficient is calculated from sample data, we denote it with the letter R. If the correlation coefficient is calculated from population data, it is denoted with the Greek letter rho. The correlation coefficient will always take values between -1 and 1. The absolute value of the correlation coefficient tells us about the strength. Correlations with absolute values close to 0 suggest a weak or no association, while absolute values close to 1 suggest strong. The sign of the correlation coefficient tells us about the direction of the association. Negative values suggest a negative association, and positive values suggest a positive association. Further, the correlation coefficient has no units of measurement, and if we switch the response in the explanatory, the values will not change. Located here in the picture are some different examples of values of correlation coefficient. So, for example, notice that this association here is negative and moderate. So we see that we have an R of -0.8. This association down here in the corner looks like no association, and notice that its correlation coefficient is very close to 0. In this plot right here, we have a positive association that is fairly strong, and notice that R is positive and close to 1. Cautions. The correlation coefficient is only a valid summary when the association is linear. You must plot your data before computing it to make sure the association is linear. We should always plot our data. The correlation coefficient is sensitive to outliers. And again, you should plot your data to see if there are any outliers. Recall that an outlier is an observation that lies outside the overall pattern of the other observations. Another way to determine if a point is an outlier with respect to a numerical summary is to remove it and see if the point would substantially change the results of the calculation. The Pearson correlation coefficient is the most often reported when the data is continuous, and it is reasonable to assume the variable has an approximately normal distribution. However, if one of the variables is not continuous or does not come from an approximately normal distribution, the Pearson correlation coefficient may not be appropriate. A Spearman rank correlation coefficient is appropriate to compare variables of interest as long as they each have an ordering without any other assumption. Recall the serial dataset for Module 7. The dataset contains information about 77 different types of cereal and their dietary information. We're going to look at variables sodium and rating. We want to see if the amount of sodium can explain the consumer rating of cereal. The scatter plot is given here. Notice that the scatter plot exhibits a moderate weak negative linear association. Looking at the plot, along the x-axis we have milligrams of sodium, and along the y, the rating. And again, we have sodium here because we're going to use sodium to explain the rating. We see that the points go down and to the right, suggesting the negative association. This association is linear, and we say moderate weak because the points are not tightly clustered together. Pearson's correlation coefficient R equals -6.894 in this example. This value supports what we visually see in the scatter plot. Your turn. Here's a scatter plot which displays the number of abortions performed per 1,000 women versus the percentage of women in a country who live under liberal abortion laws. So, for example, we could find the point representing Oceania, which is located right here. In Oceania, about 75% live under liberal abortion laws, and we see that along the x-axis. And there are about 16 abortions per 1,000 women, and we can see that by looking over to the y-axis. Take a moment and answer the questions located on the script. After you've finished, come back and we'll look at the answers together. Based on the plot, what are the explanatory and the response variable? Notice here that since the percentage of women living under liberal abortion laws is along the x-axis, that is the explanatory variable, and the response will be the number of abortions per 1,000 women aged 15 to 44. B. Give the percentage of women living under liberal abortion laws and the number of abortions in South America. So the first thing we need to do is find the point corresponding to South America, which is located right here. And notice that this point corresponds to a percentage of about 12% and about 33 abortions per 1,000 women ages 15 to 44. Describe the direction, strength, and form of the association in the plot. Well, we notice here the direction is negative because the points go slightly down and to the right. The strength here would be moderate or weak. And the form here is linear because these are in a rough line. Based on the plot, is there a pattern suggesting that as the percentage of women living under liberal abortion laws increases, that the number of abortions decrease? Well, notice as that percentage goes up, we do find that the number of abortions is decreasing. So the pattern does exist. In part E, can we conclude that the liberal abortion laws are causing the decrease? Why or why not? And the answer here is we cannot prove that because this is an association. Associations never tell us about causation. We would need to know more about the study and whether or not an experiment was performed. Predicting the outcome of a variable. Suppose that a new cereal with sodium content of 105 milligrams per serving is about to be released. Can you predict the rating? We can use the scatter plot to help us. In order to use the scatter plot to help us, we need a way to summarize the information contained in the plot. When the points in a plot have a linear pattern, we can use a regression line to summarize the information. A regression line is a line that best fits the data in the scatter plot. It is also known as a least squares line. When there is a single explanatory variable, equation for this line can be written as follows. Notice here is the equation, and the equation involves three different pieces. We have y hat, which is the predicted value of the response variable, a, which will be the intercept of the line. Notice that this line is going to be found using sample data, so a will be a statistic. And then our third piece is b times x, where b is the slope of the line. The regression line can help us predict the rating of a type of cereal given the sodium in a serving. For the cereal data, our response variable is rating and explanatory sodium. To make the equation easier to read, let's replace y hat with ratings hat and x with sodium. So here's our new regression line. How do we find the slope and the intercept? We'll use software such as R or SAS to help us find them. In Module 9.3, you'll see how to do this. Using a computer, we can find that A is equal to 95.788 and B is equal to negative 0.497. Replacing them in the equation gives the following. We can use this equation to help us predict the rating of a cereal with 105 milligrams of sodium per serving by setting sodium equal to 105 and solving for rating hat. Here we find that the predicted rating of a cereal with 105 milligrams per sodium per serving is equal to 43.603. Notice that the predicted ratings all fall on the line. We can use the plot to predict the rating of the cereal with 105 milligrams of sodium per serving. We can find the prediction by drawing a vertical line at 105 milligrams per serving, found here. Notice that the vertical line intersects the regression line at 43.6. This is the same predicted rating we got using the equation. The line and the equation contain the same information, but the equation will give you a more precise value since the line requires you to look at the graph and estimate the value. Definitions. The observed value of y is the response value observed for a data point. For example, each ratings of the cereal in the data set is an observed y. The predicted value of y hat, is the response value that would be predicted for a given value based on the line going through the points. For example, any predicted rating you could find using the line or the equation. The regression line is a line that makes the predicted values closest to the actual values. Looking at the serial example, residuals give us a way to compare the observed y's to the predicted y's. The residual for each data point is given by the observed minus the predicted. We can also say that the residual is the vertical distance from each point to the line. Looking at the scatter plot for the sodium example, notice here we have the regression line. So all of the y values that fall along the line are the predicted y's, and then all of the dots represent our observed data points. So looking at this data point right here, this data point is given by xy, where y is its actual observed value. If we look at the distance from this point to the line, that distance is the residual for that point. The goal is to make all the residuals as small as possible. We can do this by drawing the regression line, again known as the least squares line, which minimizes the sum of the squared residuals. So what your computer is doing when it finds the regression line for you is it's finding this line when drawn through the points makes all of the possible residuals as small as they could be. So notice if we had moved this line up, we would have gotten closer to this point, but we also would have gotten further away from these. Realistically, when we collect our data, there will also be limitations since we are only looking at a sample and not the entire populations. Thus, we can never really know the true value of the response for each value of the explanatory variable. Instead of a true value, we rely on the values we observe in our sample. Hence, we use residuals to estimate error. The error is the difference between the observed value and the true value. Simple linear regression defines a statistical model for a linear relationship between the response variable and the explanatory variable, represented by the line, plus random variation, the errors. The statistical model is given by the following. Notice here that y is the response variable. There's no hat on it. This is our actual y's that we could observe. Alpha plus beta x is the relationship between the explanatory and the response variable, and epsilon is the random error. Since this model describes the population, the slope and the intercept are parameters and are represented with the Greek letters alpha and beta. Using the data, the true values of alpha and beta can be estimated. These estimates are given in the regression line that we discussed earlier. So notice that A is an estimate of alpha and B is an estimate of beta. In order to use simple linear regression, we need to satisfy the following assumptions. The subjects in the sample are independent from one another, and the errors come from a normal distribution with mean zero and constant variance. Regression is a wonderful tool because it can help us predict what will happen when we don't observe every possible value of the explanatory variable. It is one of the most commonly used tools. As with any tool, we need to make sure that it is appropriate to use. So we have some guidelines for using regression. One of the most important things is to plot your data before using a regression line. Regression lines require a linear association. A computer will calculate a regression line for you for any set of two quantitative variables with the same number of values. It's up to you to decide if it is reasonable to use the output. Regression lines are only useful when predicting values inside the observed range of the explanatory variables. With a serial data set, we would not want to use the line to predict a rating of a cereal with 200 milligrams of sodium per serving because the largest sodium content in the serial data set is 160. This would be known as extrapolation. Outliers can have a large impact on the regression line, and it's very important to make sure you do not switch the explanatory and response variables. The regression line will not be the same. What else can a regression line tell us about the relationship between two quantitative variables? The slope and the intercept of a regression line also hold valuable information for summarizing the variables. Each has its own interpretation. Slope. Slope is the predicted change in the response variable y given a 1-unit increase in the explanatory variable x. For the serial data set, the slope tells us that the predicted change in rating each time the sodium content in a serving is increased by 1 milligram of sodium is a 0.497 decrease. Intercept. That's the predicted value of the response variable y if the explanatory variable x is equal to 0. it doesn't always make sense to set the explanatory variable equal to 0. For the cereal data set, we do not have data at 0 milligrams of sodium per serving. Therefore, it does not make sense to interpret the intercept since this would be extrapolation. Recall the correlation coefficient from earlier in the notes. There is a connection between the correlation coefficient R and the slope of the regression line. For more information on regression, there's a series of videos that you can watch from Khan Academy. A link to these videos is located in the video script. Cautions when analyzing associations. When exploring the association between variables, there are common pitfalls that you want to avoid. We're going to look at 3 of them. 1. Extrapolation is dangerous. Extrapolation is using a regression line to predict y values for x values that are outside the observed range of data. This is very bad practice. Be cautious of influential outliers. Outliers can be influential, which means that they have a large effect on the results of the regression analysis. To be influential, the x value is relatively high or low when compared to the rest of the data, and it must fall quite far from the trend that is shown by the rest of the data. When these 2 things happen, the line tends to be pulled towards the data point and away from the trend of the rest of the other points. Correlation does not imply causation. Correlation association does not imply causation when 2 variables are associated. Other variables may have influenced that association. We can never determine causation based solely on a plot or a regression line. We must know about the study. This concludes the Module 9.2 notes.